Hello everyone, today I will introduce the programming of resistors. So we double-click the resistor. After entering, let's introduce the above part first. Introduced from here, then to the right, and then these. Here is the coordinate information of the component. There is X, Y, and angle information. Then corresponding to the MARK1 used, MARK2 for this information. The main editor's information is here. This is a puzzle, a size 10 puzzle. The type of resistor used. It's got a resistor capacitor transistor in it. And SOP, KEF-N, LED, connectors. If this is a resistor, you choose a resistor. If it's a capacitor, you pick the capacitor. If this is the case, you choose KEF. What type it is, what type of components do you choose? This window is called FOV. This window is called FOV. Now it's a resistor. We choose the type of resistor. And here's its component number. We copied it. Then paste it into the component library. The purpose of this is to have the same component numbers. When we finish programming this component, other components with the same name are also programmed at the same time. It means that as long as it is this original number, same number, I only need to make one. Just complete all the components with the same name. So we put it in the component library. Next time if you make another new program, as long as there is this number in the component library, it will also automatically complete the programming of this component. So when we finish making it, we need to update it to the component library, and we don't need to make the program next time. He has no image now. He's going to give him an image. So we are going to click and create a new window. Then select a region, this region. This area image is the template image he needs to upload later. This image is used as a reference image. We enlarge the area of the window, and the window should fully wrap this component. You don't need to choose any algorithm for this. We can choose this. This algorithm has no detection function because we selected areas. It just saves the picture. Save the picture and send it to the maintenance staff for viewing. It is for the person at the back who judges good and bad products to watch. This is a standard reference picture. That's what it means. This standard picture. We need to choose a standard image, not a bad one. Okay, so we can click here for an updated metafile library. Let's click. Yes. Then it saves the picture of the resistor. So we created a standard image. This picture will be sent to the judge in the back. After the AOI machine inspection is completed, a standard reference picture will be compared with the actual test picture for the judge. Therefore, we choose a standard image. This reference picture is used as a standard goods product for inspection by AOI judges. Before talking about the detection algorithm, so let's start with a vector. Let's create another window. Detection of ontological defects. We are going to talk about this vector, because this is important. Whether the machine has false positives or not also has a certain relationship with this vector. We first choose a detection algorithm. So you can see here, this is the output vector. This is the output vector, which is to output a coordinate or target point. This is the call vector, where the target of the vector to be traced is selected. Suppose we are. It is the welding point that detects the resistance and detects the welding quality. This window is the solder joint that detects this resistor. Check whether the welding is qualified. Check whether this resistance has any problems such as air welding, fake welding, virtual welding, etc. Let's give this window a name and choose an appropriate one. My English is not very good, so I need to find the right name. We put this detection window here, the soldering area of the resistance. The main purpose is to detect the welding quality of the resistor and whether the welding is reliable. Place the electrode position of the resistor. You see, it's placed here. Suppose this resistance welding inspection window is placed here. Suppose there is a problem with this resistor placement, and the placement position is shifted to the left. This occurs if the detection window does not have a call vector. Since no vector was called, the detection window remains in its original position. He will appear like this. The detection window is not in the correct position, so the detection is incorrect. Since no vectors are called, the coordinates of the detection window remain unchanged. Now, when the resistor is placed, the placement is offset. This phenomenon occurs. Therefore, this detection window needs to call the vector of the resistor. When the resistor moves to the left or right, the detection window will also follow the resistor and move the same distance. When the detection window calls the vector, regardless of where the resistor is placed, the detection window remains on the left and right sides of the resistor. Which vector should be called? This mainly depends on which output vector you choose. Almost every algorithm has an output vector. It depends on which one you choose. Not all inspection windows require vector calls. Some inspection windows prohibit vector calls, such as those used to detect placement offset issues. If you call the vector used for the distance detection algorithm, there will be no offset issues. The welding quality of this detection resistor needs to be moved along with the resistor, so a vector is required. If the resistor output is vector 1, then the window for detecting resistor welding must call vector 1. These two are the vector and output vector we need to call. For each detection algorithm, the left side is the call vector, and the right side is the output vector. Okay, now we're going to talk about detection algorithms. We need to determine whether this resistor has shifted. We want to determine whether the resistance is offset. We need to refer to this pad coordinate position. Refer to the position of the pad to determine if it is offset. Therefore, we must first identify the grab pads. Identify the location of the pads. So we had to choose the name, which we called bad pad. Select this. The first detection algorithm we need to do. This algorithm is to detect whether there is a problem with this pad, and use the pad as a reference position. We use the pad as a reference for the output vector of the coordinate position. We choose RGB light source. This is our ordinary 3-color light: red light, green light, blue light. This is usually used. This mode is RGB. What detection algorithm do we choose? We usually choose this. This photo mode. This photo mode. then this box. And the yellow box is the CAD frame. Then we put the checkbox and click on it. Click on it to move to the center. Frame this pad. We click XY to align. OK. The XY coordinates are aligned with the CAD coordinates. This is a simulated light source. We can choose from different light sources. RGB analog light source. This is a simulated light source. This purpose is mainly to make the image feature points more obvious. Bad features are obvious, and AOI machine recognition is more accurate. We chose it. You look at the pads and around the pads. Select the appropriate light source, mainly to distinguish it clearly from this pad. To compare the display, the comparison shows that in this way, the AOI machine can recognize more accurately. It would be even better if there was such a clear distinction between black and white. We can debug it. Let's make it bigger. We choose different light sources to match the brightness. Switch between different light sources to view. Let's see which distinction is more obvious and better. We mainly weld the blue parts. Bring out the blue. Something like this. Just like this. After the light source setting is selected, try again. After the light source is debugged. Because this is the first detection algorithm, so we don't need the call vector. And then we pull up the recognition window. The recognition detection window is the same size as this pad. If the window is not aligned, we can also move it by using the keyboard arrow keys. After the detection window is as large as the pad, we click on the pickup window. So this is picking up a template. When the AOI detects a resistance, the detection algorithm compares this template with the actual resistance. After the pickup is completed, this window now becomes a search window, and we will enlarge the search window. The search window will refer to the following template for searching. The search window will automatically select the target based on the template and set parameters. He will look for the corresponding target in this search window. The window we enlarge or reduce is the search window. The upper limit setting for this parameter is 100. The lower limit setting is 65. As long as the actual parameters are within 65100, he determines OK. As long as it is above 65 and less than 100. And he decided that it was OK. These two are the parameter offsets set in the X and Y directions. Since we use the template as a positioning function, there is no need to check the offset, so this parameter does not need to be changed. We only need to output a vector target. Vector target 1. The output of this vector 1 is used for subsequent detection algorithms, used to call the following detection algorithms. The following inspection algorithms will move according to the vector 1 output by this algorithm. Assuming that the actual target moves to the left, vector 1 will tell the following detection algorithm that the inspection window should move to the left. Okay, now let's do another detection algorithm. Another detection algorithm is used to check for resistance offset problems. Detect the X, Y offset, angular offset, size and shape difference of this resistor, etc. The resistance to the left, right, front, back, and the angle offset can be detected by any distance. Select bad ontology name. Choose this algorithm. This detection window should also be X, Y aligned and centered. X, Y alignment is aligned with CAD coordinates. Then choose which light source is suitable, and the contrast is obvious. Double-click to switch. We use this light source to fabricate the detection algorithm. Do we need to select the vector 1 we just output? We don't choose. Then shrink the window to match the resistor size. As big as the resistance size. Then, click on the pickup window. After clicking on the pickup window, the window becomes a search window, and we expand the search window. We are now starting to debug the algorithm so that it can automatically identify targets. We're going to move this brightness line to the right. This line is placed on the far left, so I need to hold down the left mouse button and move it to the right. What color is this resistor now? We will double-click in this color area to select the corresponding color. We're going to double-click the color area to select. Let's pull down the color area window a bit to see the effect. Because we need to identify the solder joints at the positions of the two endpoints of the resistance. So the bright areas we're going to pull to the brighter areas and move to the right. You see, when I was debugging, there will be changes here. When we are debugging color and brightness, the following parameters are changed simultaneously. Debugging the parameters here is equal to modifying the size of the area or window on the right. We exclude very dark areas. Remove low light areas. The resistor has two soldered endpoints. This to parts. It doesn't recognize it now. Because resistors are two solder joints, their colors are not connected together, so we have to enter 2. Then, enter 1 for consistency. The algorithm automatically recognizes it. It is important to note here that entering 2 means there are 2 colors that are not connected to each other. If you enter 1, it means there is only 1 color, which is a hole. If you enter 3, it means there are 3 separate areas of color that are not connected to each other. Please note the pink areas, which are divided into 2 parts, so enter 2. My brightness should be adjusted to 255. Set the darker part to 127. If you cover the entire resistor with pink without dividing it into separate areas, then you set 1. Now the pink color is divided into 2 areas, so set it to 2. Then, we want to set a range of resistance offsets. It is the offset distance of the allowable resistance X, Y, and angle. Meaning, we allow the resistance to be offset in the range of X, Y, and angle, and we set a parameter. We set a suitable parameter, such as 300A. Micron. This is a micron. 0.3 is too small. It should be set to 350 or 400A. Because it's measured in microns. Y direction settings 350A. The actual detected parameters only need to be within this range. He's fine. Now this window turns blue. Explain that the parameters meet the range requirements, which is no problem. You look at its actual range of X and Y, which is not exceeded. We also need to set a parameter, angle. The resistor rotation angle is not higher than 3 degrees. This is the angle at which the resistance is checked. Its angle cannot exceed 3 degrees, and you can set the required parameters. Allowing differences can be set to 5. This difference in size becomes larger or smaller, the difference in the shape of the resistor. The parameters shown in green are the actual test results. This is the detection algorithm to check the resistance, X, Y, angle, and size differences. We will center the inspection window in X and Y. These are the actual test results. We want to output a vector, select vector 2. Vector 1 is used by the first algorithm, so we output vector 2. We now output vector 2. Now, the algorithm is programmed to look something like this. The algorithm is to detect the XY of this resistor and the offset of the angle. Other chips and components are also tested in this way, such as resistive diodes. Suppose the resistor has shifted beyond the range we have set, the algorithm will alarm. Okay, this algorithm is introduced. Let's update the component library so that components with the same name can be made simultaneously. Because it takes a lot of algorithms to detect a resistor, we will introduce this first today. Today, this X-Y angular offset detection algorithm is introduced. We click to update the component library. Then exit. OK, save. You see, as long as it's the same component number, he automatically edits it. We can put this window. The zoom is the same size as this pad. Why haven't other resistors with the same name changed? We didn't update the component library, so it doesn't change. We double-click to enter. Update component library. OK. There are still many detection items that have not been introduced, and we will introduce them later in the video. Because of time constraints, we will introduce this algorithm today. I will introduce these two algorithms today. One is the photo positioning method, and one is the detection of the offset. Okay. All the windows have changed. Why is the angle of this resistor like this? It's because the Gerber file I used is incorrect. The CAD coordinates I used are not from the pick and place machine. It comes from Gerber. Because the CAD angle is incorrect, so this will happen. So why do I suggest that you must use the CAD coordinates of the pick and place machine? Therefore, it is necessary to use CAD coordinates. Otherwise, we need to manually modify the angles one by one. Because I used the solder printer template file to modify it. So this problem arises. The video is introduced here. If you don't understand anything, you can contact us at any time. I hope you can like and support us. If you are interested in our videos, please follow and subscribe to us.